Is this better? Yeah. Okay. So let's start. So welcome to the school. This is the school. As you probably know, this is the Penn State campus you're on right now. This is the first annual School of Information Theory organized by me. I'm Eileen Jenner from Penn State and Gerhard Kramer from Bell Labs. Just a few quick remarks before we get on with our first lecture. Just the idea of this, just a quick history. This is actually an idea that existed since the early 90s in Europe, called the Winter School of Coding and Information Theory. Has not been tried until today in North America. So we started thinking, a few colleagues started thinking of bringing this to North America, I'd say December 2006, around that time frame. It was proposed to the Board of Governors of the IEEE Information Theory Society sometime in September of 2007, and they lended us their support generously, and we started organizing this event, which you're in today. So hopefully we're making history today. This is the first annual, but we certainly hope there'll be a second and a third and a fourth and so on. Okay. So let me first thank the people who worked really, really hard for this. First, I want to single out my assistant, Debbie Lauder, who's worked really, really, really hard on this for a number of weeks now. So let's give her a hand first. Thank you, Debbie. And so she worked on everything that went onto the registration packet, as well as everything that went into your stomachs and will go into your stomachs. So it's very important. Also, I want to acknowledge my students who, I guess in the past few months, have been ignored. Their meetings have been canceled, and instead of being angry with me, they worked really, really hard on the local organization. So please stand up, guys. Min Chan, Ertuğrul Çiftçioğlu, Xian He, and Ye Tian. Also, our organizational committee, student applications, Şenur Ulukuş from University of Maryland, Ivana Maric from Stanford. For publicity and web, we've received a lot of help from Nick Lanneman from Notre Dame, Lalita Sankar from Princeton, and Brooke Schrader from University of Maryland. Before I go on, I guess I'd like to just personally thank Gerhard for doing a lot of work for the organization along with me. I guess the next one goes to our instructors. Hopefully on Friday we'll say this was a success, this event, and that's largely due to our instructors who so generously devoted or volunteered their time to come and teach these lectures. Today we're going to hear from Muriel in network coding. Tomorrow is David Shea with network information theoretic topics, and on Wednesday it'll be Toby Berger with bioinformation theory. As well as on Thursday we'll have a keynote from Vince Spoor. And so we thank all of them for volunteering for this event. Also, a big thank you to our sponsors. The fundraising effort essentially started as soon as the preparations have started back in October of 2007. And without these sponsors, we wouldn't be here. First and foremost, the Information Theory Society, who supported us both morally and financially in a very big way. Again, stuff that's going into your stomach and so forth. DARPA also, Princeton University Electrical Engineering Department, Penn State University Electrical Engineering Department, and Penn State University Networking and Security Research Center, which I'm a member of. So the next item is we've communicated to you via email that the response has been overwhelming. We started this event thinking that this will be a 50, 60 student tops school, and we ended up with over 160 applications. And so the original budget was done according to a smaller scale, so we communicated to you the difficulty in possibly giving travel grants to everyone. We're still working on that, and there's going to be a form on the school website with which we're going to gather information from you pending what we hear from our sponsor, potential sponsor. Okay, so watch out your mailbox and the web form, and we'll communicate this to you after the school concludes. Some local information. You've all registered, so you've all received this registration packet. Inside is some useful information, including the maps, the restaurants. You're on your own for dinner tonight and tomorrow night, so the restaurant list should be helpful. There is a detailed program that you can see. There's an attendee list, so you can talk to each other during and after the school. There's food in 101. I think you've already figured that out, in the next building. There's going to be a banquet on Wednesday evening in Nittany-Liinen, where we had the reception yesterday. Very important point, parking. Don't park on campus. You'll get towed, you'll get tickets. This is a very interesting, unique situation here. We're in the middle of Pennsylvania, yet we don't have parking. If you must drive, if you're staying at a hotel that's not walkable, then please do park in one of the downtown parking structures. Closest one is on Fraser Street, which is between College Avenue and Beaver Avenue, I think next to Allen Street. That's just a regular public parking. Wireless access, we will have wireless access. Again, you need to all get an access ID to be able to connect to the Penn State network. And during the coffee break, you can go and see our system administrator, Ms. Marcia Church. She will be sitting in front of 101 E East, where the break food will be served. And if you show your photo ID, she'll give you access so you can connect with your wireless. Question? All right. And as I mentioned, we have an attendee list in the registration package. The program, which you already have in your packets, is we have the opening remarks now. We'll start with the lectures very soon with Muriel. And then this evening, for about 2 hours, we have student presentations. These are the 10-minute talks, followed by the very important Society Student Committee meeting, which most of you know I chair. So the idea here is just to talk, since there are so many students already here, to get your input about what we can do for the future events and basically get you to volunteer, which I will do. So stay after the student presentations at 6:30 in this room. We'll have a meeting. Tomorrow we'll have David, who's going to give us 3 lectures in deterministic models and scaling laws. And then we'll have student presentations again. On Wednesday, we have 2 lectures from Toby on bioinformation theory. And now we'll have a panel with our instructors and Gerhard, and I'll moderate the panel. And we think it's going to be interesting. We hope it's going to be interesting. And then we have student posters and presentations, followed by the banquet. On Thursday morning, we have the keynote from Winsport, followed by student presentations, and we will conclude the school at 6:10 p.m. on Thursday. Okay? So for presentations, you know that each of you who are attending are either presenting a poster or a short talk. The talk length is 10 minutes. Don't go over. We'll cut you off. This includes maybe a quick question also. So the idea is to get you to try to intrigue your colleagues just enough so that you guys can talk afterwards. Okay, very short talk. Poster sessions, we have 2 sessions, each 90 minutes length. You should go and see the other posters and also talk to everybody. An important logistic point, the day of your poster session, Ye, could you stand up? Please see Ye in the morning. He'll collect your poster and we'll set it up before the poster session starts so that everything goes smoothly. Okay? Just the day of your poster. And so finally, instructions for you. The purpose of this is not a regular conference. The purpose of this is to facilitate interactions between the students and instructors and senior attendees. So use this opportunity to learn from Muriel, David, Toby, Vince, any other faculty that's going around. We'll all be happy to talk to you about your interests, the problem you're working on. Learn from your fellow students. Start talking to them. Talk to people you haven't talked before. Right? Meet with people. Try to meet as many as possible. Learn about each other's work. and ask questions. People love to receive questions. I love to receive questions. And you'll get their attention. And finally, enjoy your time here. That's the most important. So I'm just going to conclude by saying that we're dedicating this school to Sergio Cerveto. Most of you have heard of him. He was a good friend and a colleague, and he cared very much about the student student committee and learning in general. And he really wished that this school became a reality. So we're really happy that that's the case today. So with that, I'll leave the remarks to Gerhard.
Put that on. I'll speak loud enough.
Okay.
Give me one of them.
I think
the other one.
Yeah.
Okay. Well, you're not going to hear anything coming out of here because this is meant for the microphone at the back. So there's 2 microphones here. So for myself, also to you, welcome to the school. And I hope you guys can learn something while you're here and also get to know each other. And this gives me the opportunity to say thank you to Eileen. Although she said I did quite a bit of work, she did way more. She was involved in doing all the local organization, making sure you get fed, making sure the rooms are here, and together with Debbie, really put in the bulk of the work here. So thank you, Eileen, for doing that. This now gives me the opportunity to introduce Muriel briefly. Muriel is a professor at MIT, as I think most of you know. I think I got to know her first in 1997. That's what I remember in Ulm at the ISIT. And so it's been, I've known her for 11 years. She's accomplished a lot since that time. And I guess all I'll say is that we're very happy to have you here. And yeah, wish you the best.
Thank you. Well, I think you can hear me, right? So I'm going to turn that off for feedback, or there's no...
No, you need...
Can you guys hear me with this one? Yeah, I think it's...
Yeah, this one goes to the recording. So there's 2 separate ones, unfortunately.
Should I wear 2?
Yes.
All right. There will not be feedback is the positive side of it, because there is... Okay, great. Well, my goodness, quite a get up. Anyway, thank you, Eileen. Thank you, Gerhard, for inviting me. It's just, I'm really, really happy to be doing this, both because, you know, here I have a captive audience. I can talk to you all day long. But also because I think this is just a fantastic, not just technical event for our society, but also a community building event, and I really, really look forward to spending these days with you guys. As Eileen said, I like questions, right? So feel free to ask questions, and as a matter of fact, I am also quite open to changing a bit the flow of the course. If there's particular interest in something or disinterest in something else, you know, we can definitely be very flexible. We're among friends, and the point is for you to get the most out of this. So it's going to be an introduction, and this is, as you know, I collaborate with a lot of people, but many of the slides here also come out of work, you know, a course that Ralph and I co-developed for several years now in a variety of guises and incarnations, but also slides with my former students Tracy and Desmond. I really need to put up my collaborators. I've put sort of in bold the ones from whom you know, a lot of material in this course is coming from. But I have a lot of collaborators. I'm very, very fortunate. And whenever I talk, obviously, you know, I'm presenting the slides, but that all these people are behind these slides. Thank you very much. Okay, so, yes. Woo! All right, great. And I have a mouse. Ooh. You know what? I think only one input is all I can handle. I already have 2 outputs. Okay. All right. Thank you. Okay. Okay. So, I see what you say. Yeah. Well, that's all right. Okay. So this is the outline of the course. We'll do an introduction to network coding, give the network model, and obviously take a very algebraic view of the whole thing. We'll talk a little bit about delay issues, but this is something that will be returning. You know, delay is something that I'm going to have a bit as a leitmotif, because I think it's very important when we consider network coding, particularly how network coding is different from traditional routing. So much of the morning will be fairly, fairly devoted to setting these foundations and some of the algebraic aspects. And then we'll go and talk, after sort of a very general overview of the algebraic aspects, we'll go and talk a bit about distributed randomized coding. After that, what I'm going to do is sort of move a little bit more towards, I mean, one of the fantastic things about network coding, in my opinion, is that it really naturally straddles traditional networking and information theory. Right, so I'm hoping that this course will reflect that. And after doing what would be considered as, traditional networking or fairly traditional coding, we'll move on to aspects of optimization, which then go and reach much more into what would be considered, optimization for networking, Bellman-Ford, and so on. So we'll talk about that. Particularly, we'll go a little bit into distributed optimization, a little bit of issues of mobility, touch upon compression. Again, since I said network coding has all these very nice combinations, we'll talk but on the more on the optimization side as to how it relates to compression. And then in the afternoon we'll go into the non-multicast case. We'll kind of have set it up a little bit here in the morning, but we'll talk more about it in the afternoon because it's a very good example of an aspect of network coding which has strict, if you will, pure information theory or algebraic aspects that many of which have not been resolved, and all the way to just a plethora of opportunities for all sorts of intelligent heuristics, which I think our community has a lot to offer to the networking community. We'll talk again a little bit about delay, particularly in the aspect of wireless downloading. So it'll be again of a bit of trying to bring together the information theory and the networking. And then if we have time, we'll go into network coding and security, again according to time and interest. So this is the broad outline of the course, and what I've tried to do is balance some sort of thematic progression with my unwillingness to do sort of all algebra in the morning, all networking in the afternoon, and then something else, right? So I will still be roughly that, but I'll try to interleave it a little bit to keep your interest and to show better how all these things are really not separate in my view, but married very well. So here's a canonical example, which by this point I'm sure everybody in this room has probably seen or heard of, and I'll still go over it. The idea here is, of course, I have a source. This is what sometimes people call fondly the butterfly. I have a source, and I'm trying to broadcast 2 bits. It could be 2 symbols, obviously, from that source S to these 2 receivers Y and Z. So I have bit 1 and bit 2. So what's going to happen? Obviously, I'm going to send a bit down one side and a bit down the other side. Let's assume I have a capacitated network. Otherwise, it's trivial. I could send it all down one route. And this capacity basically only allows me a single symbol. So at T, obviously, I'm just going to take what I got and broadcast it out. Same thing at U. And then the thing that I need to do is make a decision at W. Well, the kind of decision that I'm going to make at W in a traditional sort of store and forward, what I would call more the transportation model, which has been prevalent in networks, is that W would have to make a choice, and there would be a switch here. I mean, a router is really just a switch with something to control the states of the switch. There would be a switch which at least temporarily would connect this input to that output and ignore this input with respect to that output. So of course, in that case, Y would be just getting 2 copies of V1, Z would be getting B1 and B2, but Y would not be happy. So what to do? Well, let's just linger on this one a little bit more. Of course, in general, we don't have a one-shot network. Right? In general, we have some sort of time evolution of the network. So you could imagine, well, if this is a router which allows the switch to go into different states, what we should be doing at W is sometimes sending B1, sometimes sending B2. That way, sometimes Y will be happy, sometimes Z will be happy if what I have is really a flow of bits. But that means that half the time Y is getting everything, and half the time it's not. Same thing for Z, which means that I would get a flow of 1.5 to each. Okay, so I can do that. I can definitely get a flow of 1.5. But as you all know, what I should do is make use of the fact that I'm not transmitting, oranges, apples, or whatnot. I'm transmitting bits, and take the sum, right? Module whatever field I'm working in. Take the sum, and transmitting the sum at X, I will then have at Y and Z, instead of having 2 different symbols or 2 different packets, what I'm going to have is 2 equations. And I'm going to solve those equations. And in order to get what I want, I'm basically going to just get B2, add it, subtract it from B1 plus B2. Same thing here at Y with B1. And that way I'll get the 2 symbols that I wanted. So when we're going to talk about symbols, you can think of packets. Obviously later we'll talk about issues of how does one actually construct packets when one is doing network coding on them, and so on and so forth. Okay, so here's a problem description, and the framework I'm going to be borrowing very much from the paper that Ralph and I first wrote in this area, got us interested in this area. So we have this little example, and I had to tell you, so when this example first came out, I remember Ralph said, Bruce Hayek said this is a good thing to look at. And I said, well, okay, let's look at it. And we didn't immediately go to that. We instead did something very different, which is we tried to map it to Sonnet, which is an optical networking standard, right? So, but very soon, once we convinced ourselves that it worked in Sonnet, it was important to set it up in something which makes sense, both from a traditional networking sense and from a traditional information theoretics perspective. So what do we have when we say that we have a network? We really have a graph, and here we're going to be considering directed edges. There's work on undirected graphs, but I'm not going to have time today to go into that. And so I have these edges, and I'm going to have capacitated edges. So what's a network? It's a set of nodes with the corresponding edges. And I'm going to have a set of source nodes, and I'm going to have a set of sink nodes. And obviously, the source nodes is where data comes into the network, and the sink nodes is the nodes at which data needs to be received. And of course, a node can both be a sink, and a receiver, for instance, that one. Okay? So what do I mean when I'm saying that I have transmissions? It means that I have inputs which are random processes. Okay, so at an input, I have a set of random processes. And for instance, here at node V, I'll have mu V random processes, which are coming in, x1 through x mu V, obviously also parameterized by V at that particular network. And I'm going to call that cal x. By the way, I'm going to say cal. I'm going to use LaTeX in English to denote this animal here. Okay, and I'm going to have a set of random processes which are output, which I'm going to denote by z, with cal z being that set. And then the edges in the network, of course, carry random processes themselves. Right? And that's basically how we get stuff from input to output. And what does it mean for me to set up a connection? For me to set up a connection going from node V to node U, okay, it means that there is, first of all, a random process, which is part of the random processes that originate at V, okay? And that random process, if the connection is established, is also part of the random processes that is observed at the output U. Okay, so that means what it's a connection, right? The random process that started out at V ends up at U, right? Somehow, through the magic of these Y's, all right? And I'm going to call cal C a set of connections, and the network coding problem is the following. I give you a graph, I give you a set of connections. Can I spit those connections established or establishable within the graph. That's it. Right? So if you're asking about capacity, it would basically be trying to span the whole set of this Cal C. Right? If I was asking what's the capacity region of the network, you're basically asking what is the space of all these Cal Cs. Okay, so this is it. You know, we've set up the problem. Okay? So now the problem is very general. And one of the things is, first of all, is it solvable? Second of all, how do we find a solution if it's solvable? We'd like to do that. And everything that we're going to be doing here for a while is going to be very idealized. But you'll see later, as we go more to applications, that a lot of this idealization either can be taken away, or it doesn't really hurt. It's not that big a deal. So one of them is synchronization. By the way, this is something that throws off people very often with network coding. People say, oh, but wait, do all the packets have to get there on time at the same time? And the answer, of course, is no, and we'll see that later. There's no issue of protocol here, how we found out that a packet was from a particular user, whether that packet was really getting to where it was supposed to go. How do I find out that it got to where, we're ignoring all of those issues, although, again, we will visit these issues later in the day. Dynamic behavior we're not dealing with, but we'll talk about it. Error-free operation, that's a big thing here. We're assuming error-free operation. We'll look later at erasures. We won't have much, and if we have time towards the end of the day, we'll look at issues of error correction and network coding. But pretty much we're going to be error-free, except when we go to erasures, which, by the way, makes, of course, a lot of sense in a packetized system, since you would very often deal with the erasures, deal with the errors at a lower layer, and if you cannot correct them, declare an erasure to the higher layer. But basically, what we're going to do is going to give insight into possible limits and opportunities. Okay, so let's go to more simplifications, because again, we've set up this very general problem. It's a little daunting right now. I'm going to set up all the links to have the same capacity. I can always have parallel links, so that's not much of an issue. All the sources to have the same rate. Again, I can have parallel sources. I'm going to choose the X's to be mutually independent. We'll look later at the case where the X's are not mutually independent but are dependent. Okay, but let's not leave them to be mutually independent. And then we're going to have vectors which are going to be symbols of length m, elements in F to m. Okay, so just a string of bits. And basically, we're going to make our lives very easy for the time being, just so that we can really play with the structure of the whole thing, rather than get bogged down in generality, which we'll see later can be added gradually. So I'm going to choose all operations at network nodes right now to be linear. Okay, we're not going to cover it in this course, but it's known that for the multicast you can always do that, and we'll show later in the day that for the non-multicast linear is not sufficient. But right now we're going to just restrict ourselves to linear and just again try to understand a bit the structure. So what do we mean by what's going on at an edge? Well, an edge is going to have a set of inputs from other edges, what I'm going to call endogenous inputs from within the network. And it's going to have inputs that originate at that edge, right? Because at that node, because that node can be a source. And then it's going to put out on any outgoing edge some linear combination of those exogenous and endogenous inputs. Okay, that's what's going on here. And of course, I could have other edges, and they would have the same or different combinations. So everything's very mild up until now. Anyway, I should have a place to look at the time. I don't know if there's so I don't run over. You know what? I'll get out my BlackBerry. So if I look down, it's not because I'm doing email. Okay. Although if you see me typing, I am. But it's because I'm looking at the time. All right. Okay. Great. I go until 10:30. Is it or 14? 10:45. 35. Wow. Okay. I'm getting. Okay. So I do feel like Bob the Builder. These things. Okay. So what does a receiver do? Well, a receiver gets inputs, And obviously, it's not trying to receive the input that originates there. Maybe it is, in which case, that we don't have much help to offer it. But it's really trying to get these inputs from these edges that are incident on it. And since everything has been linear, obviously, it can always, if it can undo it, it can undo it linearly. Right? And it's trying to recreate some sort of process, or create some sort of process, the Z's, remember, that's what we called the observed processes, which are going to be linear combinations of their inputs. Okay? So everything's going to remain linear, and therefore, of course, we'll have easy conditions for invertibility or inability to invert. So let's go through this simple example. It helps to go through a little example. I mean, it just... So for instance, here I have this little baby network, and it has x1 and x2 coming in here, and this is the input node, this is the output node. So what does it mean when I'm saying that I'm taking these linear combinations? Well, over here at E1, obviously the only things that I can mix are x1 and x2, so that's what I have. Same thing for E2. If I look now at E3, it only has a single input, so it can only carry whatever y is being carried on E1, possibly weighted by something. Same thing on E4, because it only has E1 de facto incident upon it. Over here, I'm going to have two inputs, E2 and E3. So for E5, I can mix E2 and E3. And then the Z is going to be some linear combination of E4 and E5. Z1 is going to be a linear combination of E4 and E5, and so is Z2. Okay, so it's just applying what we just saw. So, you can see right away that, of course, I don't want to be, sitting there writing equations. I should put it in some sort of matrix form. Okay? So if I look at what the matrix form is, I have a matrix here which is just the weighting that's being, if you will, the pre-processing that I'm doing on x1 and x2, the weightings that I'm giving to the x's. A matrix here which is a matrix describing the effect of the network. Okay, so what do I have here? I have beta E1, E4, beta E1, E3, E3, E5, E1, E3, E3, E5, right? I have E2, E5, right? And then you look at this and go, well, actually, this matrix is really giving me all the different paths that there are to get from this input node to that output node. Right? There are no other paths. Because of the directionality, I can't go this way, for instance. Right? So this little matrix G here is, in effect, the matrix that's reflecting the structure of the network. The topology of the network is being reflected in this G. And then this matrix here, the A, is just the post-processing that's being done at the receiver node. Right? So right here, these alphas are just the processing because it's what I'm going to apply to whatever was received, pre-processed, gone through the network, post-process. And what does it mean for me to be able to recover Z1 and Z2, X1 and X2, make the Z1 and it makes the Z1 and Z2 map back to X1 and X2? Right? Well, this is not the guy that's worrying me. I can choose my epsilons however I want. This is not the guy that's giving me trouble either. The only guy in here that can give me trouble is G. Right? Because it's the only one that I don't completely have control over. Now, I can control the betas, but for instance, I can't put an entry there. It doesn't work with the topology. All right? So what am I going to do? I'm going to be able to invert the whole kit and caboodle, this whole BGA, if and only if I can invert G. Right? So let me deal a little bit more with this matrix G that's there in the middle. I mean, right now, the way I describe the matrix G is I just said, look, here's this matrix G. I could kind of stare at it because it was a small network. And I said, I could just go in with my little finger, just point to, I'm first going to this node, to that node, blah, blah, blah. And you can imagine doing that, right? But you'd like to have a more systematic way than running around it with pointing my finger. So really, since this is a matrix that arises out of the structure of the network, I should be able to look at the incidence matrix of my network Okay, and if I look at this incidence matrix, I'm going to have zeros across the diagonal. But basically, what I really care is what edge is incident on what edge. Okay, I have 5 edges. I mean, the nodes are really just there to tell me here that, edge 1 is basically incident on edge 3. Edge 1 is not incident upon itself. It's not incident upon edge 2. Edge 1 is also incident upon edge 4, but edge 1 is not incident upon edge 5. Right? And same thing for all of these things. So if I look instead at a line graph where I'm looking at the incidence of the edges upon each other rather than the nodes, since what I'm really saying is this edge is able to carry contributions only from this edge, whereas this edge 5 is able to carry contributions from edge 3 and edge 2. Okay? Then how am I going to describe the effect of going through the network? Yes? So let me repeat the question. So the question was, what do I mean by incident? So incident means that the second term, so if an edge is an ordered pair of nodes, right? Well, here I could have parallel edges, so there would be a numbering within that, but you get it, right? That the tail of one edge is the head of another edge, right? So that the random process being carried by one edge, if it's incident upon another edge, can have an effect on the random process that's going to be carried on the second edge. All right? And when I go through the network, what I'm doing is I'm basically stepping, every time I go through the network, I'm stepping through this network one step at a time, and every step that I take through that network is controlled, is defined in terms of its possibilities by this matrix. Yes?
So these gains, they are implicitly assumed to be dependent only on the graph topology and not on the type of pattern.
Can you repeat your question more loudly?
Here you are implicitly assuming that you are going to use the same gains for all kinds of patterns.
So
Vila coefficients are only dependent on the structure of the graph and not on the packet type.
So let me try to rephrase your question. You asked, am I changing the coefficients according to the data?
Yeah.
In this case, I am not changing the coefficients according to the data. We will see that for multicast it is not necessary. Okay? But, you can argue later. I mean, it's interesting, because later when we look at erasures, right, to some extent we're going to say that if the packet didn't get there, it's as though we gave it a 0 weight. Right? So you can argue at that point that it's, you didn't see it, or you saw nil data, and therefore you assigned a coefficient that was 0, as though the packet had gotten there and you had given it a 0 weight. But you're absolutely right. In this case, I'm just saying that I have a graph, and that on this graph there are certain betas. Okay? Very good. And the betas, so it's not that I'm implicitly assuming it, by the way. The betas were never defined as a function of y. So it's explicit, but you're right. Okay? Is there another question? Yes?
Are you going to post it on the website or something like that?
I can post it, or I can flood your inbox, whatever you like. All right. So, okay. So, yes, so we observe that, okay, so every time you go through this network, you basically, well, you could do nothing, right? You could just stay where you are at the beginning, or you could step through it once, or you could step through it twice, and so on and so forth. Basically, you can step through it as many times as you want, and it's that stepping through that's going to create the total effect of going through the network. Okay? And you know that if I have 1 plus x squared plus x to the cube, blah, 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 it's like 1 minus x inverse. Well, the same thing happens with matrices, right? If I have I plus f squared, blah, 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 I get, just like the Taylor series expansion that we know and love. So I'm going to have here this g, okay? which is a polynomial in F. Okay, because I can only keep going so far. I mean, eventually I get from one end to the other, right, through some way, shape, or form. Yes?
Why have this F squared or F cubed? Because if you don't have a feedback, how come you have this like IR cubed?
You're asking, so every F is one step through the network. There's no feedback here.
So how come you have F squared?
Why would F squared be related to feedback? I don't get it.
No, I mean if you feed these back to the...
I'm not feeding anything back. I'm stepping through, right? I'm stepping through. That's to say that if I'm here, one step will get me here or there.
I think maybe if I can rephrase the question, how do you get the, I think there's an underlying overall linear equation that you then get the I minus F inverse.
You do. There is an underlying equation, which is basically what I didn't rewrite because it would be very large, which is that I'm really looking at a matrix, edge-to-edge matrix. I'm looking at a line graph. Does that answer your question? Okay, but there's no feedback assumed here. Okay, and you should not see this. There's nothing here. I'll talk later about cycles. Okay, does that answer your question? Okay. Thanks, Gerhard. Yes.
In the addition here, this is really addition mod 2 to the, not mod 2 to the m, but MGF 2 to the m.
Yes. Okay. Yes. We won't get to security, but that's okay. I'd rather have questions at security. Okay.
Okay, talking about this 1 minus F inverse, there can be two ways to interpret this thing. One is Taylor series extension. The other one is that it is basically all the paths.
All the paths, that's right. Yes, that's exactly it.
I just wanted to know what was your motivation by it. So like you can think of this in two ways. Either all the paths in the graph or an Taylor series extension.
Yeah, they give you the same thing.
Exactly. They give you
Right.
What was your motivation?
My motivation?
This is like a research exercise.
My motivation was to get something that worked. I mean, well, I mean, obviously, as I said before, you could look at it and then go with your finger and then you say, well, really what it is, it's induced by the incidence matrix where, I'm looking at a line graph, the incidence of the edges, and therefore you write it this way. So I didn't answer your question, but I mean, you're right. That's the point that I was madly trying to make, but maybe not effectively, is that having this expansion is the same thing as going through with my finger and counting all the possible mappings, right? I mean all the possible paths to get from the input to the output. Does that make sense? Yeah, but I mean that was what you're saying. That the motivation was basically we're trying to get. I mean, look, the motivation was to get a clean algebraic expression of what was going on, so that then you can apply other techniques and do something with it. So, yes?
All this analysis, I think it applies only for acyclic graphs.
Right now it is a cyclic, that's correct. We'll look at cyclic later. We have to put delay to make cyclic. Okay, so that's why right now there's no delay. So absolutely, yes, that there are cyclic. Thank you for pointing that out. Because right now we have no delay, right? It's an instantaneous one-shot deal. Then we'll look at delay, and then when we put in delay, we'll put in cycles. Okay, thank you. Yes? Yes. Okay, so, all right, so 1 plus, okay. So, all right, so let me look at this matrix over here, okay, and then we'll go back. So what I said is originally I showed you, what we were looking at was this matrix. So is everybody happy with this matrix? Should I go back to this, or is everybody happy here? Everybody's happy here. So the thing that was happening here is that I was looking at going node to node. I was looking at all the paths node to node. And now maybe, the funny thing is I had an intermediate slide with the with the edge, with the incidence graph, and I thought, no, that's too ugly. I'll take it off. But I should have left it. But basically, I have an incidence graph here where if I look at the edges as being nodes, by saying that there's a node such that, so for instance, let me just do a part of the incidence graph. Here's right now E1, E4, and E5. Okay. Thank you. E5, right? That's what it looks like. Right? And what I'm going to say is, actually I'm going to turn this into E1, okay, E4, E5, and E1 is incident upon E4, and E1 is incident upon E5. Have people seen these kinds of transformations before? How many people have seen these kinds of transformations before? Okay, so not everybody, but okay. So basically, that's what I'm doing. Okay, so I'm turning it into this kind of graph, right? And so you can imagine that I can do this to the whole thing. Okay. Now, to that graph, once I've turned it into this incident, what I'm going to do is I am going to, I can describe the incidence on this graph. So this graph, as you see now, because I had 5 edges to start out with, I have 5 nodes on it. Okay? Whereas I started out with 4 nodes. I now have 5 nodes because I have the edges, right? And on this graph, I basically write all of these. I write this. So if I was only writing an incidence matrix saying, in the traditional networking sense, instead of having betas there, I would have a 1. Right? It would basically say that there exists an edge going from this node to this other node. Okay? But because I'm going to allow myself, and basically that's a lot of what network coding is doing, incidentally, is going away from switching matrices, okay, to matrices in which I have different weights other than 0 and 1. Okay, but let be that as it may, all I'm saying is I'm allowing some beta which is non-zero, whereas the topology of the network forces me to have zeros at these other locations. Okay? Does that make sense? Right now, for this matrix. So is everybody happy, before we go on, is everybody happy with this matrix? Yes? Okay, now there were 2 questions. Yes?
Why is that matrix not invertible?
No, I'm not dealing with F. I'm not dealing with that. So let's not go into the structure of F right now. Let's just understand where F comes from, then we'll talk about invertibility. Okay? Yes?
It doesn't look like you actually added I into the P matrix. I mean, that looks like that's the sum of F and F squared, and so without the I.
Oh, you're right. I left off the 1s over here. That's my fault. Absolutely. That's a typo. Thank you. There should be 1. Okay, that's what was confusing you guys. I'm sorry, that was a typo. That was a typo. Because you can always go back from yourself to yourself. So that's correct. That's correct. Yes. Wait, before. So is everybody happy right now, up until now, modulo the I? There was a question here. Adam.
No, it was just something that had initially
Yes.
confused me that, eventually, because the, plus over in characteristic 2 looks like things cancel here. Right, so really, this only works because F is upper triangular, and there's sort of this acyclic structure. Well, the same thing, the acyclic structure that means that.
Right now, I have an acyclic structure. Right now, we'll deal with cyclic structures later. That's right.
Right. So I'm looking at the transition of all the inputs together with all the values of the wires, right? And then the reason you can use addition is just all these different steps, they don't interfere at all, right? They correspond to different layers in the graph. Is that right? I corresponds to the input layer.
So I means that everybody just stays where they are. I did nothing. Okay? And then I can step through the network according to this one time. So okay, so you're right. I should have put it actually that is a type, and it's a type I've been carrying around for a while. I apologize for that. I should have put all 1s here, right? Which means I can stay where I am. Okay? I can stay where I am, and I can stay where I am here. Okay? Thank you. And then I go 1 step, right? Which is from 1 to 3, or I can go 1 to 3 to 4, 1 to 3 to 5, E1 to E3, E3 to E5. Okay, so I just keep, does that make sense? Every time I go through F, I step through the network once. And at the end, I can step no more. Right, once I end up over here, I can step no more. So the most I can step through the network is going E1 through, the longest path length that I can have is 3, right, which corresponds in my graph over here to going from E1 to E3 and E3 to E5. Yes, Lalita?
Okay, so I'm confused. Does the F have 1 along the diagonals?
Yeah, I should have put a 1, which is just staying right where you are.
So what does that mean? An edge is incident on itself?
It would mean that basically you would just have, so, well, the ones, basically, okay.
Only in P, right?
Yeah. Pardon?
Only in P, right? There are no ones in F.
Well, you could have the edge incident upon itself. It actually would make no difference in the end.
Well, wouldn't that be cyclic?
Yes, but it would not make any difference, except that then I could cycle forever.
Put coefficient 0.
I could, yeah, which makes no.
The same as
That's right. Exactly. Okay, so it would make no difference in the end. Okay, which is why I should have put it here because it makes it clearer, but it makes no difference. Okay? Yeah? Okay. Any more questions? No, this is good. Yes?
Does it always take this nice triangular form?
No, it does not always take this. We will see others. Okay, this is just an example. It takes other forms. Okay, you can come up with any network and you can make it, and you can see that it's not going to take just this form. Okay, so, okay. Yes, Adam. No, that's fine.
I mean, doesn't it have to be upper triangular given the graph is? I mean, under some, you can sort the graph, right? Is there no cycles?
In this case, there are no cycles. Yes, later we will see other forms of this. Okay.
So it always will have that. Nice.
In this case, well, no, because I could have. So here you're right. I'm sorting the cycle. I'm sorting the graph E1 to E3, E3. So that's right. I am sorting the graph. But later if we had I could have right. So in this case it is because I have no cycles. But later we will add cycles. Okay. So I don't want you to think that they're always upper triangular. But then we have to add a D. Is everybody happy? There are questions back there. Yes? Oh no. Okay. Just running. Okay. No questions. Running. Yes. While we're at it. Hey. Yeah.
I understand now what you mean. So that P matrix is kind of like the overall connectivity.
Yes. Oh, not just connectivity, but paths through, right? The F is the connectivity in terms of just the topology. Yes.
So the P matrix has kind of hidden in the framework that there's some delays happening here.
There are no delays here. Okay. That's right. So I'm not taking delay into account because I have an instantaneous. So I have a stepping through, right? But I don't have. I basically have an instantaneous model where I don't have a delay in the sense that I'm saying, and this is a good point. Imagine that instead of having a delay, I have a continuous scheme, right, in which I've decided that I'm going to become completely delay insensitive. I'm not going to change anything from one point to the other. Okay, so the delay, you're right, is kind of built in. No, it's not a repetition code. Oh, excellent. It's not a repetition code. Okay, it's not a repetition code. It is an invariant code. Right? So instantaneously at any node in the network, I'm taking the process that is coming out at that point and mapping it to the next point, but I'm always doing the same thing. Right? So it's the same thing for me to look at a one-shot that's been running forever. Right? You see, that's a very good point. I never did. You see, I didn't tell you much about these processes. See, there's a lot sort of built into here, and these random processes, right? Okay, and I've assumed, like I said, I assumed synchronization, I assumed, everything was fine, right? So imagine that because you're right, there is a delay in the sense that it's been stepped through, but because all I care about is the total y at the end, I can do a one-shot description of what's going on in the network because I'm not going to change what's going on in the network. Does that make sense? So if I wanted to clutter a little bit more, I could have put a t here in discrete time, right? So I could have put an x v1 t over here, right? Which means that the output at t plus 1 would have been like the t, but because it's not changing at any one point, I can just look at it as a one-shot. The beta is invariant. Oh, the data is flowing. It's a constant flow. So it's just like we do in information theory all the time, right? I mean, we have, for instance, we'll have a multiple access channel, for instance, and we say, y is equal to x1 plus x2 plus noise, right? So there is an implied, because it's one shot such that because it's going on forever, I can do the one-shot representation the same way that I can do the indefinite representation. Now later I will look at the case where I put in a delay, right? So for instance, you could imagine something where a particular path for whatever reason is going to have another delay, and that delay will be necessary when I look at cycles, right? Because when I look at cycles, and I no longer have this upper triangular nice type of matrix. But again, I don't want you to think all matrices are upper triangular. Okay, the little ones we want. Okay, then I have to take the delay into account, right? Because otherwise I would have non-causality, right? But right now I'm taking a one-shot view, which is the same as taking the long-term view in a statically set up network. Okay, so just like what we do in information theory all the time. Is everybody happy at this point with this? I really do want to take all these questions because, yes?
So you said that having the one diagonal, the zero diagonal is exactly like one diagonal, right? And doesn't really change a lot.
Well, but basically, let me put it this way. It would make my life harder right now, but I could do it.
Yeah. But doesn't that change the spectral radius of the matrix? Which means like you have to take again.
So again, that's right. Which is why I didn't do it. But I could put cycles in it right now so that it is incident upon itself. And maybe from just at this right now let's put it this way, from a teaching perspective, it seems like maybe it would have been easier. But it's not going to give me anything, and I would have had to use more machinery.
So my question here again is by changing the spectral radius and by
well, okay, let's not talk about the spectral radius of the
just because of the Taylor series expansion. So in order to be able to write that
I would have had to use more machinery if I put in a 1. Okay, so you're right. It's not really a typo. It's a typo in the way that I showed it because I didn't tell you how I'm dealing with a finite field. Okay, I think that's the main thing. So to make things much easier, I should have put it here in a continuous setting with a 1, and then told you how I go from the continuous setting to the finite field, right? So I should have put the 1s, it would have made it easier. But actually, this is right now, because I am over a finite field, okay? And basically, the only places I can go, since I'm not allowing self-cycles, which I should have allowed self-cycles maybe to make it nicer, but I'm not allowing cycles here, I'm allowing cycles later, okay? I should have put the 1 and then said, but because I'm in a finite field, I'm stepping through, these things keep adding to each other, and therefore, in the end, I'm going to get nothing else. Does that make sense? Okay. I mean, the problem is I haven't told you, I could do this with a lot more rigor in F2M, right? But then we would have to spend at least an hour, 2 hours on Galois fields. So I'm assuming that, but okay. But you're right. The way it looks, it looks like a typo right now because I didn't tell you how I did it. Okay, and so maybe I should have put the 1s, but then I would have required more machinery, or I should have, from a teaching perspective, maybe I should have stayed in the reals and then said, but because I'm in a finite field, I can do this. Okay, but this is right. Okay, this is right. Is everybody happy? Or not? Any more questions? Yes?
I don't know what you mean when you say it's right.
Can I quote you on that? I love it. This is correct. You know, this is the F, and yeah. Basically, yeah. So basically, what's going to happen is I'm not allowing these step throughs, okay, and okay. So you what do you mean by what? Yeah.
The way you've written it, I mean,
yeah.
P equals I plus F plus F squared, that's not equal to this matrix, right? So
There should be a 1
Yes,
on the diagonal.
there should be a 1 on the diagonal. So it is a typo in the sense that should have a 1 on the diagonal. And I should have put 1s here, but then I would have required me to put some other machinery to deal with the cycles, which I don't have right now. Okay?
So should I interpret that?
So it is right. So as I said, I do have a typo in the sense that I should have a 1. Okay? But it's in the sense that I don't give a hoot about the diagonal. Okay.
I guess I don't know what we're going to do with this matrix exactly.
Yeah, that's right. So you're right. I should have a 1 as it is written. I should have a 1. Okay, but I don't care about the diagonal. And then I really should have put a 1 here, but it would have made my life harder in terms of the cycles. So for right now, let's imagine that I have a 1 here, and this is right in the sense that this is going to do everything that I need. Okay, but imagine 1s along the diagonal. Yes.
Write out a matrix of a vector of length 5 with the elements E1 to E5 in it.
Yes.
That vector will be F times E plus some other matrix times X1.
That's exactly it. Yeah.
And then you see immediately where.
Yeah, and I had that, but it was so ugly that I decided to take it out. Do you want me to just pull up that slide, maybe the one that I took out? It would take a while. Let me see if I can pull up the slide, or maybe I can pull it up later. Okay, but basically, yes, that's exactly it. I have a matrix of the length 5, and I'm applying F, and then I can keep applying F.
So E equals
F
times E plus some matrix times X.
That's right.
And you bring the other.
And you can keep going. Yes.
Invert to get E.
That's right.
That's where the
Exactly. So like I said, there should be an I. I didn't put it in there, but it doesn't matter. It's going to work. Okay, but I'll bring up later at the break. I'll bring up the full slide where I had done the whole thing. But I thought it would be so ugly that nobody would want to see it, so I decided to jump those 2 slides. But is everybody happy at this point still? Yeah. Okay. So you see that I should have the I there, but basically I'm not going to care about it. I should have the I. I should have the diagonal. Okay, so it is a typo, but it's a typo in the sense that this is not going to matter. Any more questions? No? Does everybody see? So every time I go through F, I am stepping 1 time through the network, 1 step through the network. Yeah? Okay. Can I go forward? No, this is really good. This is... Okay, good. Okay, so let me look at a linear network system where I have X's coming in and Z's coming out. And I have this input vector, X, which is exactly what Gerhard was bringing up. So this was the example that I thought would make everything clear, but obviously maybe I should have done this before doing the example. And then I'm going to have an output vector, okay? And the Z, which is the output vector, is going to be some M times X, okay? And this M times X is the pre-processing times going through the network times the A. All right? So the elements here of this whole matrix M, which I'm going to call Xi, are alphas, followed by all the betas, which is the stuff that's going on inside the network, followed by all the epsilons. Okay? And let's go back here into what's going on. This G of T is going to be this I minus F to the F transpose inverse, and I'm going to call that the G of T. Okay? And for cyclic networks, the elements of G, and hence of M, are polynomial functions in these variables Xi1, Xi2, and so on. Which means, again, going back to this example that made people so happy. Okay, and again, just imagine the ones, but it makes no difference. Okay, having the ones, and that's what I mean by this is basically right. It makes no difference. Okay, in the development down the road. Basically, what it means is every time I do F, I am stepping one time. Right. So if you have the identity, means I can stay where I am. But you know, again, this goes back to this issue of cycles. It's just going to be a pain. I'd have to develop more machinery. It's not worth it. Okay. Or I can say, well, you know, if I am right now at edge 3, the only thing that I can do is go to edge 5. One step through the network at edge 3 only gets me to edge 5. If I am over here at edge 1, I guess if I had put in the ones, I could go back to myself, which you know, it's not actually going to give me anything down the road. Right? I mean, you see why with the ones, it's not going to give me anything down the road. So you're right, I should have the ones here. It's a typo, but down the road, it's not going to give me anything to be able to come back to myself and just sit there. Okay? But from 1, I can't go to 2. I can go to 3, or I can go to 4. Okay? So again, if I have the vector here of the processes y on each edge, right? It's a 5 tuple for y1 through y5 for the processes at each of those, right? The way that the process at y3 maps onto onto other processes y is through beta E35. Okay? All right, so basically what we've done is rewrite this whole thing. Okay? So the way that the process, so you see what I have, the reason I had the zeros 1 is because I didn't have any ones with ourselves. Right, so having the 1 in this would say that I can say that YE4 is equal to beta E1, E4, YE1 plus, you know, some factor of YE4, which is always true. But you see why it doesn't help me, right? So I might as well set that factor to 0. Right? But if I wanted to have that diagonal, and that tells you what I mean by it's basically right. If I wanted to have that diagonal populated by something, it would be the same thing as saying, for instance, let me just concentrate on this one equation here. It would be the same thing as saying, you know, y of E4, and by the way, I don't have to populate with 1s. So obviously, I would have to populate with, you know, some factor. That y of E4 is beta E1, E4. As a matter of fact, it would not be good here to populate it. Times y of E1 plus beta E4, E4. Y of E4. Right? This would be what the E4, E4 would be what's along the diagonal. I can do that. Right? And it would give me the populated diagonal, but it would not help me in the end. Is everybody happy with that? Okay? Okay. So, right, so what I did in effect is I took a matrix representation so that I have the mapping of these x's and y's, the y's onto the other y's. Right? So I have the mapping of the x's onto the first y's, right, which happens with the pre-processing, and then the y's upon each other, and then I'm mapping the y's onto the z's with the post-processing. Okay, which is the matrix of the alphas, betas, epsilons. The whole thing, the whole kit and caboodle of going through the network is going to be a polynomial in these alphas, betas, and epsilons. Okay? So going back to this example, this YE5, if I were to plug in for YE5, I would plug this whole thing in. So I would have something which is a multinomial in the epsilons and the betas. And then I could plug back in what YE2 and YE3 is. And then I would have more beta factors and then alpha factors. So the z's, in the end, can be mapped all the way back to the x's multiplied by alphas times betas times epsilon. Okay? And all I'm trying to do is sort of separate the pre-processing, the post-processing from the G matrix, which comes out of the F. And each F is one step through. Right? Allowing that, I should have probably left the self stepping through, but this would not give me anything. I would just have to keep track of these things. Okay? All right. So for acyclic networks, the elements of G are going to be polynomial functions in these variables xi. We remember xi includes the pre-processing, the processing inside the network, and the post-processing. Right? So I have now an algebraic characterization of flows. The z's are a sum of x's multiplied by factors which are products of xi's. So this is important. Is everybody happy at this point? Yes?
So you said each multiplied by f means stepping through the network once, and the example you gave, it seems like you can step through at most 3 times. So what does like f to the 5 mean?
Well, what does it mean?
Because there's only like 3 times.
That's right. Right. So that's it. I stop. Right? But I don't know a priori. See, I have a general formula, right, which is no matter what the depth of the network is going to work. But I do stop at some point. But that's the number of times that I can step is part of the structure of the function of the f.
Still get I minus f inverse.
Again, it goes back with this I. See, if I have I can keep going until I'm blue in the face, which is why I didn't want to keep it. But yes.
I'd like to make an observation.
Yes.
Is going to be,
Sorry, can you guys keep it down because I can't hear the question? Yes.
I think n is going to be 0 for.
Alicia. Yes.
I think n is going to be 0 for n greater than 4.
Yes.
I think that's
Yes, that's exactly what he's, yes. Right, because of the structure of f, I can only keep going, and at some point I stop. So now I'm mapping to nothing. I can't, right? But once I've stepped through, see, and again, this goes back into this 1, which would be a pain to have. Once I get to here, there's no place for me to go. If I leave this diagonal, I can keep going around myself, right? Or I can, right, it would not go to 0 if I leave the diagonal. I could keep going around myself, or I could take forever to get there, which is again back to the very nice question before about the, the built-in delay, which I'm not looking at explicitly, right? Or I could take forever to get there because I could loop around myself indefinitely before getting there, right? So if I had the non-zero element there, it would not get to 0 because I could always loop around myself. But because I have the zeros element, it is 0. I mean, at that point, I can go no further. There's nothing for me to map onto, except the z's, the post-processing. Okay? Yes?
This matrix P was always reversible, right?
Pardon? No, it is not. We shall see.
Okay, so this example it is.
Yes, of course, in this example, it is. Now, in this example it is. Now, let me ask you, why is it invertible?
Because it's acyclic, right?
No, it's not invertible necessarily because it's acyclic. Pardon? Because I was able to keep the inputs. So this is a very good point, right? I could give you something which was acyclic and not invertible on this one. Can somebody tell me right away an edge that I could take out here, keep it being nice, obviously, if I take out an edge, and make this thing not invertible? Pardon? E1, E5, that's right. Oh, no, E5, that's right. Pardon? E2, that's right. How about one that I could take out and keep it invertible? E3, right? So the invertibility is a function of the structure, and this is crucial. What we're going to be doing in a few slides is that we're going to be mapping the invertibility of this matrix to the ability of the network to map to have the z's map back to the x's. Okay?
What is it? I mentioned invertible.
Okay, so as I was saying, if I had left the beta E4 here, yeah. Pardon?
I'm still talking about
P that's defined as the infinite term.
I'm creating a P here, which is a polynomial in F.
Yeah, that's what I'm talking about.
But it's my G. Okay, so I put P to show that it was a polynomial in F.
So, yeah, so you said that it was, the question was, is G invertible?
Let's hold that question. I'm going to go into that question, okay? But I just want everybody to realize right now, the fact that G is invertible or not invertible is not a factor of the cyclical or non-cyclical approach, right? I think everybody responded at the same time. If I'd taken out E4, there's no way I could map back Z1, Z2 to X1, X2. If I'd taken out E3, I would still be okay. So it's a function of the topology, okay? So let's hold that. There were two questions on invertibility. Let's hold those, okay? So here's my condition. Let a network be given with a source and a sink. One source, one sink. The following three statements are equivalent. The point-to-point connection is possible. The min-cut max flow bound is satisfied for a rate which corresponds to the cardinality of cal x going from V to V prime. That is to say, all of the total rate coming into V going to V prime. Because remember, I restricted myself to sources of rate 1. Okay? So let's go back to this example. Let's go back to this example. What's the cardinality of cal x here? Everybody tell me to make me happy. It's 2. Good. All right. All right. Or the determinant of the transfer matrix M. This transfer matrix here, right, which is a 2 by 2. Is non-zero over the ring of polynomials defined with respect to this xi vector. That is to say, I can choose xi's such that I can make the matrix invertible, right? Now, I can always choose xi's in a stupid way. Right? For instance, I could have chosen my betas here to be 0. I'm not going to get far. Okay? Now, obviously, that's a blatantly stupid move, right? But maybe there are moves that are less blatantly stupid. Right? So now the question is, I'm going to have a set of xi's that I'm going to have to pick because it's static, which, as you pointed out, are not data dependent. Right? And for multicast, it wouldn't have helped if it was data dependent. Okay? And I'm going to have this set of xi's, as we're going to show basically. I'm going to have this set of xi's, and from this set of xi's, the set of xi's is the network code. That is the code in the network. So it's picking these xi's. That's the real question. Okay?